Healthcare digital twins operate by creating a dynamic, data-driven virtual model of a patient. These models rely on the continuous ingestion of high-frequency biometric data to forecast disease progression and simulate personalized treatments in real time. To secure these highly sensitive data streams across multiple institutions, engineers often propose a decentralized trust layer, blockchain networks. These networks provide verifiable auditability and secure data provenance without relying on a single central server. This split-screen diagram illustrates the conflict between these two technologies. On the left, a digital twin ingests a continuous, fluid flow of updated medical data. On the right, a blockchain locks that data permanently into an immutable chain. But when we apply actual healthcare regulations, a rigid barrier emerges: the GDPR right to erasure and HIPAA modification rules, which dictate that patient data must remain deletable and editable. The paradox is architectural. Clinical environments demand constant data aggregation, correction, and deletion, yet blockchains are engineered specifically to never change. Simply adding a blockchain layer to a hospital database creates a structural deadlock between mathematical permanence and data privacy laws. Resolving this tension requires specific engineering patterns that reconcile the ledger with the clinical need for data modification. A 2026 systematic scoping review analyzed 55 different blockchain-enabled digital twin architectures to see how developers were solving this problem. The data revealed a stark asymmetry. While there is a high volume of security-focused prototypes operating in simulated environments, there is a near-complete absence of clinically validated deployments actively used in hospitals. This heat map from the study plots blockchain functions against their level of regulatory alignment. We see a dense clustering of data points at level 1, meaning privacy compliance is mentioned in the research narrative. We see almost empty space at level 3, meaning strict compliance mechanisms were explicitly engineered into the code. Developers are assuming that because blockchains are secure, they are automatically privacy compliant. To move these systems from theoretical proofs of concept to the patient bedside, developers must build from first principles, engineering regulatory compliance explicitly into the architecture from the ground up. The baseline requirement for this new architecture is throughput. The system must process high-frequency streams of patient telemetry, like continuous ICU vitals, without lagging. This network simulation shows why traditional proof-of-work blockchains fail in clinical settings. When dense telemetry data attempts to write to the chain, the intensive computational mining required to confirm transactions creates a massive bottleneck. Confirmation times stretch from seconds into minutes, driving the latency meter far beyond acceptable clinical limits. The required structural shift is moving to a permissioned, lightweight consensus mechanism. Here, anonymous mining computers are replaced by specific, predefined trusted validator nodes, a system known as proof of authority. Because proof of authority relies on the established identities of hospital institutions rather than solving complex math problems, the bottleneck clears. The data packets flow rapidly through the trusted nodes, dropping latency to near 0 milliseconds. For devices performing continuous physiological monitoring, computational overhead translates directly to battery drain and latency. Proof of authority operates with significantly lower overhead than mining-based chains, providing the efficiency required for real-time clinical hardware. In clinical environments, the absolute decentralization of public blockchains is traded for institutional trust. This trade-off is necessary to achieve real-time predictive modeling. While proof of authority solves the speed bottleneck, the data recorded on the ledger remains permanent. This violates the GDPR requirement that patients must be able to delete their records. This expanded architectural diagram maps out the solution: a hybrid on-chain and off-chain storage model. The incoming stream of patient data approaches a fork, explicitly separating the biological payload from the verification metadata. The heavy data stream, containing all biometrics and protected personal information, routes off-chain. It is stored in a standard, mutable hospital database where it can be edited or deleted by administrators. Meanwhile, a secondary stream routes on-chain. This stream contains 0 medical data. It holds only cryptographic hashes, unique mathematical fingerprints of the off-chain data, and access control records. If a patient submits a GDPR deletion request, the system executes cryptographic erasure. The heavy data in the off-chain database is wiped clean, or its decryption key is destroyed, rendering the information permanently unreadable. Over on the immutable ledger, the cryptographic hash remains. However, because the underlying data is gone, the visual connection line severs. The hash is left as an isolated, orphaned reference that reveals nothing about the patient's identity. This orphaned hash serves a critical function. It provides a tamper-evident audit trail that proves a specific data transaction occurred at a specific time, satisfying the audit control provisions of the HIPAA security rule without exposing protected health information. This specific bifurcated architecture is the only design pattern identified in the literature where mathematical immutability and legal deletability can legally coexist. Securing the data internally is only half the engineering equation. The system must function inside the pre-existing hospital IT environment. This diagram shows a common failure point. When a highly customized blockchain outputs a bespoke data block, that data often clashes with legacy electronic health record systems. The data blocks fail to integrate because the formats are incompatible. To prevent data isolation, the architecture must align with established health data interoperability standards, specifically the HL7 FHIR framework used by modern medical systems worldwide. This requires the introduction of a healthcare data layer, acting as a translation mechanism. As the blockchain output passes through this layer, it is dynamically reshaped into FHIR-compliant resources that fit into the hospital's legacy input ports. Smart contracts and digital twin models must explicitly expose these FHIR-compliant interfaces by design. Adding interoperability as an afterthought leads to fragile integrations that fail under real-world clinical workloads. Regulatory compliance and system interoperability are structurally dependent. An isolated digital twin cannot inform a physician's treatment plan if it cannot communicate with the patient's main medical record. This complete reference architecture synthesizes these technical solutions into a single, cohesive clinical ecosystem. In practice, a glowing pulse of real-time patient sensor data originates at the bedside, immediately passes through the FHIR interoperability interface, and correctly bifurcates. The heavy biological payload routes to the mutable off-chain database, while the lightweight verification hash commits to the proof of authority network. The verified off-chain data and the on-chain audit log synchronize securely, feeding validated inputs into the digital twin node and generating a predictive clinical output for the attending physician. This system relies on three mandatory pillars: standard FHIR interoperability for communication, off-chain mutability for GDPR compliance, and permissioned proof of authority consensus for speed and HIPAA auditability. This layered structure provides the blueprint for moving blockchain-enabled digital twins out of experimental software labs and into the clinical reality of modern hospitals. Moving past the mechanics of technical compliance, these architectures introduce serious questions about the ethical governance of patient representation. Algorithmically mediated patient representations bring inherent risks. Predictive models can encode hidden clinical biases, and automating consent via smart contracts can shift agency away from the patient and into the hands of the administrative system. To address this, developers must integrate established ethics by design frameworks, like the IEEE P7000 standard, directly into the software development lifecycle. These frameworks translate abstract stakeholder values, like patient contestability and fair representation, into verifiable engineering requirements. Cryptographic assurance alone is insufficient for clinical trust. It must be paired with transparent governance structures that clinicians and patients can interpret and rely upon. Building an intelligent medical system means aligning the ledger's immutability with the patient's right to be forgotten, creating a structure that is legally sound, interoperable, and ethically accountable.